4.7 practice problems. The diagrams opposite represent solutes present in two different dilute aqueous solutions before they are mixed. Water molecules are not shown. When the solutions are combined, a precipitation reaction took place. Which of the diagrams is the best particle representation of the mixtures after the precipitation reaction has occurred? So we have sodium chloride and silver nitrate here. When we mix these two together, we are going to precipitate out silver chloride. Sodium is an alkali metal, so those are always soluble, and nitrates are always soluble. So those should remain dissociated, not attached to anything, and we should have silver and chlorine together. Option A, we have a bonded sodium and nitrate. We're not dissociated, so that's not going to work. Same thing here, dissociated or not dissociated ions. Here we have the silver and chlorine being the ones that are still attached. However, precipitate should be at the bottom, and that is best represented in option choice D, where we have the silver chloride at the bottom here, the sodium and nitrate dissociated and floating around. When C2H4 reacts with hydrogen, the compound C2H6 is produced, as represented by the equation opposite. The reaction is correctly classified as which of the following types? So as I look at that reaction, I am going to go from a compound to a compound plus an element going to a compound. So that could be a synthesis reaction. However, that's not one of the options here. We can look at the oxidative states of all of these. Hydrogen, when it is by itself, when just we have an element by itself, we have an oxidative state of 0. Then we have hydrogen being with a charge of +1 once it's inside of a compound, and then we can see that we have hydrogens only inside of compounds on the other side. So we do have a redox reaction present. It is not an acid base because these are not, we're not accepting protons or producing hydroxide. It's not a precipitation reaction because that's not two reactant species forming a single product is a synthesis reaction, not a precipitation reaction. Decomp, I would need one compound going to multiple. That's the opposite of what's happening. So a redox oxidation reduction reaction is the only thing that is going to work here because we do have a change in oxidative states from this hydrogen to once it is within a compound. The compound C6H8O6 reacts with I2, or iodine, according to the reaction represented by the equation above. The reaction is correctly classified as which of the following types? So I have aqueous on the left and aqueous on the right, so we're not going to be a precipitation reaction. We are producing hydrogen ions, which is a good show that we could be an acid-base reaction. We are producing hydrogen ions there. We are not producing, we have an element plus a compound going to a compound and multiple elements, all this kind of stuff. So looking at all of these, I'm also going to look at the oxidative states between everything. So I2, whenever we are by ourselves, we have an oxidative state of 0, and then we obviously are forming a charge of plus or -1 here. So looking at all of these, we have an option of acid-base because hydrogen ions are produced. Precipitation because there's only 2 reactants but 3 products. Again, everything is aqueous, so we are not a precipitation reaction. Double replacement because hydrogen and ion appear as ions in the products. We're not double replacing anything. We would need 2 compounds as the reactants, and we don't have 2 compounds, so that's not going to be an option. And then we have redox because iodine is reduced. So iodine is reduced, and so that is going to be our answer. The decomposition of hydrogen peroxide is represented in the equation above. Which of the following identifies the element that is being oxidized and reduced in the reaction? So within peroxides, oxygen has a charge of -1, hydrogen has a charge of +1, and within water, oxygen has a charge of -2. And when oxygen is by itself, has a charge of 0. So, going between these two, hydrogen maintains its oxidative state. It stays as +1 on both sides, so it was neither reduced nor oxidized. Oxygen, however, was both reduced and oxidized, so I am going to choose option choice C, where we see that oxygen was both reduced and oxidized. The titration experiment for hydrogen peroxide reacts with aqueous permanganate as represented in the equation above. The dark purple potassium permanganate solution is added from a burette to a colored acidified solution of hydrogen peroxide in the Erlenmeyer flask. Note the endpoint of the titration, the solution should be a pale pink color. Which elements is being oxidized during the titration? And what is the element's change in oxidation number? So oxidation, I should be going from a low number to a higher number. So I'm going to get rid of any option choices where that is not happening. So I am just determining between oxygen and manganese to see if that is occurring. So within the permanganate ion, each oxygen has a charge of -2. I have 4 of them, so that's a charge of -8 total. I have 1 extra negative, so that means that manganese has a charge of +7 here. Then obviously we have a charge of +2 here for that manganese. Oxygen within the water compound still has a charge of -2. Oxygen by itself has a charge of 0. So, I apologize. We also need to look at the charge of oxygen within the peroxide. So, when oxygen is within a peroxide, it has a charge of -1. And so I have the option of oxygen going from -2 to 0. That's not one of my options for my answer choices, but I do have -1 to 0, which does occur from the peroxide. So that's going to be my answer choice. Which of the following is true regarding the reaction represented above? So I'm going to look at the oxidative states of all of the reactants here. So hydrogen, whenever it is with a nonmetal, it's going to go ahead and lose that competition, so it's going to have a charge of +1. I have 2 of them, so that means selenium has a charge of -2. Fluorine always has a charge of -1. It wins. It has the highest oxidative state there. It has the highest electronegativity, so it's going to win and get whatever oxidative state it wants, which means that oxygen is going to have a charge of +1 here. Fluorine, again, -1. I have 6 of them, so that's a grand total of -6. So that means selenium has a charge of +6 here. Fluorine, again, -1. Hydrogen is going to lose that competition. It's going to have a charge of +1. Oxygen by itself has a charge of 0. Oxygen the oxidative state of oxygen does not change. It goes from +1 to 0, so that's incorrect. The oxidation state for hydrogen changes from -1 to +1. They stay the same, so no. The oxidation state for fluorine changes from +1 to -1. That's not going to be true. Fluorine, again, is the most electronegative element, so it is always going to have an oxidative state of -1, unless it's by itself, in which case it's an element and therefore would have an oxidative state of 0. The oxidation number for selenium changes from -2 to +6. That does occur. So option choice D is going to be the correct choice here. Which of the following represents a process of a species being reduced? So when we are reducing, we are going from a higher number to a lower number. So anything where we are going from 0 up the number line to a more positive number can immediately be eliminated. And so I'm just left with nitrate versus nitrous oxide here, or sulfite versus sulfate here. So looking at these, oxygen's going to have a charge of -2. I have 3 of them, so that's a grand total charge of -6, but I have a total net charge here of -1, so that means that nitrogen must have a charge of +5. Then here we have oxygen with a charge of -2, and that means that the nitrogen has to have a charge of +2. Here I have oxygen with a charge of -2. I have a total of 4 of them, so that's a -8, but 2 of them is accounted for, so that's going to be +6. And then we have again -2. We have 3 of them, so that's -6, but we have 2 accounted for, so that's going to be +4 here. So between these two, we do have some reduction happening between both sulfur and nitrogen. We have only reduction happening between nitrogen. For the sulfur, we have an oxidation reaction occurring. We are going more positive. So option choice D is the only one where we have a reduction occurring. When water is added to a mixture of sodium peroxide and sulfur, a redox reaction occurs, as represented by the equation below. Atoms of which element are reduced in the reaction? So this sodium oxide, we have a charge of, this is a peroxide situation, so we have a charge of -1 here. And then sodium has a charge of +1. So sulfur by itself is going to have a charge of 0. Oxygen in water is going to have a charge of -2. And then hydrogen is going to have a charge of +1. Sodium is going to have a charge of +1. Oxygen within this compound is going to have a charge of -2. Hydrogen is going to have a charge of +1. -2 here. So sulfur has a charge of +4. So which are being reduced? We are going down in the number line. So sodium remains the same. Hydrogen also remains the same. Sulfur goes from 0 to +4. That is a oxidation, not a reduction. And so we are dealing with oxygen only. So the oxygen within the sodium peroxide situation goes from -1 to -2 in both cases here, and the oxygen within the water goes from -2 to remaining as -2. So the oxygen within the sodium peroxide situation is the only one where we are reduced. How many electrons are transferred in the reaction represented by the balanced equation above? So we are going to go ahead and see what's going on within all of these here. So the oxygen here is going to have a charge of -2. I have 4 of them, but we have a total negative charge of -1, so that means manganese has a charge of +7. Bromine here has a charge stated, so that's going to be -1, and then hydrogen has a charge of +1. Manganese charge stated here. Bromine by itself is going to have a charge of 0, and then oxygen within water is going to have a charge of -1, and hydrogen is going to have a charge of +1. Okay, so now that we see all the oxidation states, we can go ahead and determine where the electrons are going. So electrons are being given away from the bromine somewhere else. Everyone else, other than the manganese, that's where the electrons are being transferred to, are maintaining their oxidative states. So we have 10 bromines that are giving away 1 electron each, so that means that they are giving away a grand total of 10 electrons in this reaction. Which of the following compounds at 25 degrees Celsius and 1 atmosphere contains an atom with a +1 oxidation state? So I don't really care about that first part. I'm just going to go ahead and look for the oxidative states for all of these elements. So oxygen is going to have a charge of -2. I have 2 of them, so that means that carbon has a charge of +4. Oxygen here, again, -2. I have 2 of them, so that means I have a charge of +4. -2 means that calcium has a charge of +2. -2, I have 5 of them, which means that we have a charge of -10 total, and we have 2 nitrogens to take care of that, so that means that each nitrogen has a charge of +5. And then finally, -2 for this oxygen here, and we have 2 coppers, which means that we have a charge of +1. So option choice E is going to be the only one where we have an oxidative state of +1. Which of the following is a precipitation reaction? So precipitation reactions are when we have 2 things being added together and we are producing a different state in our product. So solid plus gas going to solid, we are maintaining state. Aqueous going to solid, that is a precipitation. Gas plus liquid going to aqueous. This does look like we are producing a different state. However, precipitation reactions need to be removed from the reaction. So we can precipitate out using an evolution of a gas or a solid. It remaining within the solution as aqueous ions is not going to be a precipitation. Gas going to gas and gas, nope. Aqueous going to aqueous, no. So B is the only one where we are producing something that is removing itself from the reaction in forming a solid. Which of the following is an oxidation reduction reaction that is also a synthesis reaction? So synthesis reactions, we have multiple reactants forming a single product. So I'm going to eliminate anything where we have a plus sign on the right-hand side. And so I am left with just A, B, and E here. We are looking for a redox specifically. So we're going to go ahead and assign the oxidative states to everything. Anything where we are our own element, no charges, has an oxidative state of 0. And then whenever we are in the compound, oxygen has a charge of -2, meaning magnesium has a charge of +2. Lead has a charge of +2 here and maintains its charge of +2, and chromate is not broken up. So that means that it is going to maintain its individual oxidative states within the chromate ion. Here we have silver with a charge of +1 and ammonia, which is again not broken up, same thing that we saw in option choice B. So option choice A, where we go from an oxidative state of 0 and 0 to +2 and -2 respectively, is the only one where we have a redox reaction. So that's going to be my answer choice. In which of the following species does sulfur has the same oxidation number as it does in H2SO4? So I would need to find what oxidation state sulfur has in that particular one. So we have oxygen with a charge of -2. We have 4 of them, so that's a charge of -8. Then we have hydrogen with a charge of +1. I have 2 of them, so that is a grand total of +6 that we would need for sulfur there. Sulfur by itself is always going to have a charge of 0, so that's definitely not going to be the case. Then we have this here with a charge of -2. That's definitely not going to work. So I'm only having to find the oxidation states for the remaining ones here. So we have hydrogen with a charge of +1. We have oxygen with a charge of -2. So that's a grand total of -6 and +2. So that means that sulfur here has a charge of +4, so that is not the same. Here we have oxygen with a charge of -2. We have 3 of them, so that's -6, 2 of which are accounted for, so that gets me to -4, but I have 2 sulfurs to take care of that, so that means that sulfur has a charge of +2 here, so that's not going to work. And then here we have 2 -2, so -4. Chlorine has a charge of -1, and so that gets me to a charge of +6 here. So option choice E is the only one where we have the same oxidation number for sulfur. Zinc is used to reduce other compounds in chemical reaction. If a chemist needs a substance that is more effective at its reducing ability, which of the species would be the best choice? So reducing ability means that we are going to be giving away electrons, and so anything where we have already given away our electron is going to be a terrible choice to further reduce. Chlorine, once it stole its electron, really wants to maintain it, so it's going to be a very terrible electron donator. However, sodium, being an alkali metal, really not wanting its last valence electron, is going to be the best choice for an electron donator, and therefore going to be the thing that is the best at reducing.